Hey guys, so I'm back with the last part of the video, which is just like finishing up some of the problems that I was talking about and adding on a little bit. So first I wanted to make a really quick clarification of a mistake, and I want to explain why it's a super common mistake to make that I did when I talked about the problem that we had where we ended up, we took vector x times 1, 1, negative 1, 1, right? And we ended up with a vector x, y, negative x, y. Okay, well, the way I interpreted this geometrically was incorrect. And the reason why, and let me use a more clearer marker. That's not that great. So the reason why I interpreted it wrong is because we have to think about the fact that this is not a matrix, right? I mean, it looks like it because we've got, x, y, x, we've got two, more than one component in each row. But really, it's just that we don't know what x, y is. And really, in real life, if we did know what it was, we would multiply these two, right? And so this should really be treated as one number, which means that this is really our x and this is our y, right? Because, if we think about a vector, if we've got vector x where we've got x, y, right? We're going to treat this as x and this is y, right? So if that's the case, and we're multiplying these two things, then, which should be what we're doing, right? Because we've got, I'll draw it real quick. We've got xy times 1, 1, negative 1, 1, right? Which means we're multiplying this here, so we get 1. And then we're multiplying this, so we get negative x1, right? So this here should become addition, right? We've got x1 plus y1. So that becomes x plus y, negative x plus y. And this would become a real number. We've got an actual operation here because we've multiplied a vector and a matrix. So because of that, we treat it as one number and we treat this whole thing as the x component and this whole thing as the y component, which I know is confusing, but that means that when we draw this out, really what we're going to have is, well, if we think about the original vector was this, right? This was x, this was y. So our new x is going to be the length of both of these added together, right? So it's going to be x plus y, and that's our x. And then our y is going to be negative x plus y, which could potentially be down here. It kind of, or up here. It kind of depends which one of these is bigger. But I just wanted to draw attention to that because I think it's really easy. And I already said it was really easy to forget when you need to have like addition, subtraction, etc. signs versus not. And it's really important to sort of like always check that. But the next thing I wanted to do was move on to a couple of final, fairly short problems. So this one's super simple, but I just wanted to bring it up because it's important to know just for computational reasons. So they want you to find a scaling matrix that turns 2, negative 1 into 8, negative 4. And this is where we just like plug and chug the formulas that we were given, right? So we know that K0, 0K thing, right? So if we're trying to do that, right, we can pretty much figure out that, 2K, negative 1K, 8, 4. If we're trying to figure out, the number that we multiply 2 by to get 8 and the number we multiply negative 1 by to get negative 4, it's going to be 4. So that means that our scaling matrix will be 4, 0, 0, 4. That's really, really simple. I just wanted to show you the basic computation. The next thing is I'm just going to give some examples of different kinds of transformation matrices are, we were supposed to, the problems kind of gave you a bunch and you were supposed to categorize them as to which kind they were. And I'm just going to list these out so you can see. So like an example of a scaling that was in the book. 7007, you see how this follows the formula of having like K and then zeros. Rotation, 2, -1, 1, 2. You see how this follows the formula of like A, -B, B, A. Or was it A, B, -B, A? Let's see. Rotation. Yes, A, -B, B, A. So you see how that one follows that. You can also see, let's see, here's a shear. We haven't talked about those a ton. 1, 0, -3, 1. You see, you know, we've got the ones and then the K. A reflection. 0.6, 0.8, 0.8, -0.6. You know, you see that we've got A, A, B, B. And then finally, an orthogonal projection would be 0.6, 0.6, 0.8, 0.8. Because we don't really have a specific rule about like A's equaling B's or whatever, but there's no negatives. And that's the only one of the types of transition matrices that we learned of that doesn't have zeros or negatives. So it's got to be an orthogonal projection. So those are examples of like, you know, using those formulas to identify actual transformation matrices. So the next one that I want to do, next problem real quick, it's pretty conceptual. So it's consider two lines non-parallel, L1 and L2 in two space. So you want to explain why vector V in R2 is V equals vector 1 plus vector 2. Where V1 equals on L1 and V2 equals on L2. So they want us to sketch. So here's what I'm going to say. We start out with this XY plane, right? So we've got these two lines, right? We've got L1 and L2. So I'm just going to like make them super random. They've got to be non-parallel, right? So this is L1 and this is L2. So on here, we've got, let's place a V1 here. And let's place a V2 here. So if we take V, we can put V anywhere on here. We can put V here. We can put V here. We can put V here. But in any of these cases, we can do this, right? In all of these cases, we can connect these two vectors to that point. And that's what, you know, adding vectors is geometrically. As I said, it's when they come to a point, right? So anywhere that V2 and V1 are and anywhere that vector V is, we can draw these lines in and have them connect, which means that for any vector V, it's going to equal vector 1 plus vector 2. I thought that one was pretty interesting because it's just like good to think about conceptually. And then the very last thing that I'm gonna do super quickly is this idea of finding the determinant to decide invertibility. So we kind of already learned the equation before that, you know, A, B, C, D inverse, it has to be true that AD minus BC does not equal 0. We learned that theorem in the last chapter and we proved it. And I'm not going to go through the entire proof, but that means that we can find, to determine if things are invertible, we can find the determinants. So for example, is a reflection invertible? Well, if we've got A, B, B, negative A, that means that we can say A times negative A minus B times B, right? Because A and then negative A acts as our D, right? Minus B times C being another B. We've got negative A squared minus B squared, right? So that should give us one a -1 matrix. The reason why being that, so you've got negative A squared plus negative B squared is going to equal because we know that A squared plus B squared equals 1. We know that B equals negative A squared plus 1, right? Because, we know that this has to be true for a reflection matrix. We know that A squared plus B squared has to equal 1. It's one of the rules. But for that to be true, we have to have A squared minus A squared plus 1, right? Because then you've got A squared minus A squared. Sorry, this should be A squared plus negative A squared plus 1, because then you've got A squared minus A squared and then 1, right? So you know that B has to equal negative A squared plus 1 in the context of this problem because of this rule right here. So if we know that that's true, we've got negative A squared minus A squared plus 1. So if we know that that's the case, then that means that we know that if we've got A squared minus B squared, we've got negative A squared minus negative A squared plus 1, right? So that's going to cancel out to negative A squared plus A squared minus 1, which is going to give us -1, which is invertible because it doesn't equal 0. So to recap really, really quickly, we started out with, we did A times negative A because that's AD minus B times B, which is BC. We multiplied to, got negative A squared minus B squared. We then figured out that B squared, or that B in this case, we figured out that B squared has to equal negative A squared plus 1 because of the rules that we already know about. A squared plus B squared equals 1. So if we know that's what B squared equals, then we have negative A squared minus parentheses negative A squared plus 1, so B, so B squared. And from there, we can simplify distributing, and we end up with -1. So if we know that AD minus BC equals -1, that means that any reflection transformation is invertible. Okay, so that's basically about all that I have for us to do today. I hope that was helpful. And next week I will be back with probably some more explanations on these and then also the next lesson. Thank you so much.